Hello. Right. We'll wait until there's slightly more people. Oh, can I only do it up to 4 options? This is shocking. Hello, Denero. How are you? This is what happens when you do a poll. You think, oh, you're being snazzy, but you can only do 4 options. Horrific. Rookie streamer. No, it's only natural. Hi, Gabby. Right, I'll give it a little bit longer. Faith, you've done this years ago. Go and enjoy your evening. Right. Anyone have anything good for dinner? Or we wait for the last few votes, if there is any. I say. If not, it's just an accessible way to go through stuff, even if there's like one of you. I don't really care. So we're going to do 4 options on the poll. So the 5th one is energy changes. So like if you have a strong preference for energy changes, like go for it. You set your air fryer on fire. It's impressive. No one misses it enough to listen to a pre-exam stream when you've done the exam. Like, you're good. Right. Structure and bonding. Let's do some structure and bonding, shall we? Right. So, pretty much everything with structure and bonding boils down to, and I obviously was doing this in the week as well, about understanding the kind of what I call the flow chart. So you need to first decide, is the thing to do with metals? Is the thing to do with non-metals? Or is it metals and non-metals? Because that then affects what kind of like bonding you're going with. All right. I would say the most, I always think back to like electronic structure, and I'm thinking about like what everything fundamentally wants is a full outer shell. That's the whole concept of the entire unit, right? Is when you look at the electronic structure, you want a full outer shell. All right, that's what they want. That's what they always want. Right. So now, it's depending on what they are, is how they get it. So if you are metals, you do metallic bonding. Okay. Now, metallic bonding is where, let's say you've got your metal atom where you've got your positive nucleus and you've got your 1 or 2, say, extra. Oh, hello, Karis. How are we? Are 1 or 2 extra, which are there. Now, if I've got my 1 or 2 extra around the outside, right, in metals, they basically all kind of drift off and you end up with these kind of rows of positive ions like this. So you have your positive ions. And then the electrons will wander about. They can go anywhere, right? And because they can go anywhere and they don't stay in one place, we call them delocalized electrons. Okay, because they don't stay in one place. I always like to think about those electrons, right? As in, these are our, like, if you look at the playground, you'll have some friendship groups, right, all dotted around the playground, standing around, not actually communicating much at all. And if they all told their annoying friends to wander off, they'll go, "Oh, hello, can I be your friend?" And they'll go, "No." And they'll go, "Oh, can I be your friend?" "No." "Can I be your friend?" "No." And they just wander around the entire bit. So these electrons can move wherever. Now, the fact that these electrons can move throughout the entire thing is what then gives them the properties. So the whole point of this kind of structure and bonding flowchart is you've got your structure, and now we think, well, what are the properties? Okay, what does that mean that they actually are like in real life? Well, when it comes to metals, well, if I think about metal, we think they're strong. Okay, we think of the fact that they're hard to melt, so we've set it as a high melting point and boiling point. Okay, all things like that. And what would that suggest? Well, that suggests that the bond between those positive ions, the delocalized electrons, are strong. So that points to strong bonds / forces. Okay. What else do metals do? Well, they conduct electricity and heat well. Well, what about this structure gives that away? Okay, it's the delocalized electrons they can move. Okay, so by not staying in one place, if you put like a positive charge and a negative charge on one side, they'll flow through. Okay. The other thing they are is they're malleable. And that's because if you have a look here, they're all in a row, right? All these ions are in rows. So you can come with a hammer and you can hit it and it will just like kind of skid the row over, right? So I've got them there like that. It will kind of slide it over. And that means you can start to adjust it to whatever shape you want. So that's due to the fact that the layers can slide. Okay, so start off with the idea that we're looking at metals. They do metallic bonding. What is it about metallic bonding that translates into the real world? It's that they're strong, got a high melting point and boiling point. That points to a strong bond. They can get up to electricity and heat. That tells us there's delocalized electrons that can move. And they're malleable, and that's because the layers can slide. Then we can come to metals and non-metals, and they do the beauty that is ionic bonding. Okay, and in ionic bonding, we've got a metal, right, and that's got too many. All right, so let's say that's sodium. It's got 1 on the outer shell, right? If I want to get a full outer shell, that's the key of the whole idea. If I want to get a full outer shell, it's easier for us to lose that 1 rather than gain 7. And if I've got a non-metal, something like chlorine, right? Okay, that needs to gain 1. And they do this kind of swap. And we end up with that with nothing on the outside. Don't even need to draw the circle, but just for the sake of completeness. And that chlorine with thing. And because that's positive and that's negative, they may like to stick together. And that kind of means that they don't just do this once. You end up with almost like a chessboard, right? Where, you know, this happens again and again and again. And it even goes on in 3D, like that. Okay. And that forms what we call a giant ionic lattice. So again, what are the properties of that? What does that translate like into the real world? Well, it's got a high melting point and boiling point. So here we said that's because it's strong. So again, that means we've got strong attractions. Okay, electrostatic attractions between the positive and negative. What else is it like? Can it conduct electricity? It can't, right? It can conduct electricity only when molten or dissolved. Okay, why is that the case? Well, you've got charges. You've got positive and negative, which is what you need. And for them to conduct electricity, they need to move, and they can only move when molten or dissolved. Okay. No, Karis. So ionic is the trade. The sharing of it comes with this next one. Okay. The next one is covalent. So covalent is between non-metals, and that's where they both kind of don't really have enough. If I think back to this example here, chlorine needed to gain one. Well, if I have two of them, right? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. They're both like wanting to gain one. All right. Now there's no like handy metal here to go and trade it over, so they're both kind of lacking. Now, in the past, I've said like, let's think about how many of them are lonely. So you can see they've both got a lonely one, and that is where you were saying here, Karis, is they overlap, right? So you end up with them sharing like this. And it's kind of like a Venn diagram in maths where the things came for both, right? So here, they came for both. So I've got 1, 2, 3, 4, 5, 6, 7, 8. And on this side, 1, 2, 3, 4, 5, 6, 7, 8. So they came for both. So they've both got a full outer shell. Now, this is much more of an actual physical linkage, right? They've actually overlapped. So it's, you know, there's actually kind of a physical kind of linky bond there. Whereas here, we're just talking about positive and negatives kind of sticking to each other. This is kind of like you can see how they're bonded together because there's like an overlap. Now, there's two structures here. This is where covalent is a little bit different. We can either make simple molecules, or we can do something called giant covalent. Okay. Now, let's focus on the... Probably end the poll tonight. Look at that. Amateur hour. If I look at the simple molecules, right, they are the interesting one. They're the interesting one because they're weird. So simple molecules have a low melting point. Okay, they tend to be gases or liquids. So here we've said, well, these have a high melting point and boiling point. That tells us that there's strong forces or strong bonds. Here they've got a low one, so that naturally means that they'd be weak. That's actually not the case. If I actually look and I zoom in kind of at it, if I take like water, right, there we go, looking like Mickey Mouse, all right, between those kind of solid lines there, they are strong bonds. They are covalent bonds, so they are strong covalent bonds. But you can see here I've got weak intermolecular forces. So they're not weak per se, like the covalent bit is strong. The reason they've got a low melting point and boiling point is because of those, right? It's the weak intermolecular forces are easily broken. So even though the covalent bonds are strong, the intermolecular forces are weak, and that's when you end up with that. So that's the interesting thing I like to ask about that. There's no pluses and minuses here, so there's they don't conduct, not conduct, like I'm some kind of caveman. That's pretty much it on that. Now, when it comes to giant covalent, then, because giant covalent right, they kind of avoid the problem that this has with the weak intermolecular forces. So if I take something like diamond, again, we'll do the question on in a sec. If I take something like diamond, right, right, look at that beautiful artistic impression. But you can see how this can just keep going, right? And because of that, right, you don't get any of those weak intermolecular forces, right? It's all strong covalent bonds, right? So if it's all strong covalent bonds, then you don't get that weakness, you don't get that low melting point, you get quite a high melting point, and you also get the fact that diamond is like the strongest thing, okay, or hardest thing if I'm being technical. But because it's all strong covalent bonds, you avoid this kind of low melting point idea, okay? So let's use that. Because also, like, let's zhuzh it up here. Right? Instead of having this like lovely craft mat in the background, let's go landscape. Professional. And that's handy because where are we? Right, let's look at this question here. Let's zoom right in. Look at that. Professional. Right, so this question says, aluminium is extracted by electrolysis of a molten mixture. The rest of the question then goes on to talk about electrolysis, which is part of the chemical changes unit. However, this first bit is all structure and bonding. It says the mixture contains aluminium oxide and one other substance. Aluminium oxide is an ionic compound. Explain why aluminium oxide has a very high melting point. So we can go back to our like kind of flow chart we've just kind of done, right? So it's ionic, so we're going down the central path of ionic bonding. It's a giant ionic lattice. We see it's got a high melting point because of the strong attractions between positive and negative ions. So let's use that, right? So it's a giant ionic substance. So it's a giant ionic lattice structure. What's that going to be between? That means you've got positive aluminium ions there, and negative oxide ions. Right? What does that mean? It means that they attract each other. You get strong electrostatic, electro meaning charge, static meaning not moving, between them. And if you get strong electrostatic attractions between them, that makes them hard to break. And if they're hard to break or need a lot of energy to break, then you end up with a high melting point. Can you see that's just me formalizing and putting into words what we've just said when we were doing our flow chart? All right, like this idea of in science, you don't need to have like the snazziest answer of all time. It's this happens, therefore this happens, therefore this happens, therefore this happens, right? You can use bullet points. You don't need to be like fancy with it. That's all you need. Okay. So that's a really good example of a question talk about ionic properties. Does anyone have any questions so far? Obviously, as always, if you ever have anything, just whack it in the chat. Sometimes it will get you to kind of complete the dot and cross diagram when it comes to bonding. So you can see here, it's kind of spread over the page here. It says potassium and chlorine react to produce potassium chloride. An atom of potassium loses an electron to form a positive ion. An atom of chlorine gains an electron to form a chloride ion. Now this is really important, right? Because it's literally told you what to do. And when you actually are like doing the exam questions and you're doing it in the exam, like take the time to actually read what is going on above, because so many times I see people, right, will start reading and then you'll get mentally bored. So then you'll skip forwards to like an answer line. So this one's like doubly annoying because first of all, it's actually told you the answer in the top. And B, there's no answer line, there's a diagram to do. So many people just kind of skip through it and assume there's nothing actually asking there. It's like that picture is part of the preamble, but it's not, that's the question. So you can see here, it's got a potassium ion and it says here that it loses an electron. So that means that is going to go, right? Now, where's it going to go? It's going to go onto the chlorine. It says here that the chlorine atom gains one. Well, we can see that. So that one, I just need to draw nothing. And here, 1, 2, 3, 4, 5, 6, 7, and then that dot coming over from the potassium. Okay, and that's so easy for 2 marks, but it's so easily missed, and also like it's giving you the key ideas. Okay, that's the kind of, I would say, the real meat and potatoes of bonding. There is other stuff. There's forms of carbon. There's nanoparticles. I can go into those unless anyone has any other questions. So we can obviously continue with structure and bonding by looking at those forms of carbon, or we can kind of go on to atoms in the periodic table, because that's what other people have asked for as well. Well, in the absence of anything to the contrary, let's just crack on to atoms on the periodic table, shall we? Right. There's not a lot actually in this unit, I think. It's the real like core like meat and potatoes of it. I keep using this phrase meat and potatoes. That's one of those phrases like you've never used, and now I'm cracking into it. Let's commit. When it comes to atoms then, the first thing we need to do is be happy with the structure of an atom, with our positive protons, our neutral neutrons, and even though we've been talking about them quite a lot, stop hitting the wire, amateur hour, our electrons going around the outside. That's hopefully at this point well committed to memory. That hasn't always been the model. So there's a section, and this also crosses over with physics paper 2, physics paper 1, where it's talking about like radiation. But you need to go into like the history of the model of it. So we start off first of all with Dalton, and Dalton doesn't say atoms like this. He says atoms are solid balls. Some are heavy balls, some are small balls. Okay, but that's the point. Is he says that they're solid, and then that's how you get different elements. Our next mad lad is J.J. Thomson. He comes along and he discovers the electron. So that means that atoms can't be solid. So he says that the negative electrons are dotted throughout a kind of vaguely positive atom, right? So he says the atom itself is positive, but then you've got these negative bits spread throughout. And he calls this the plum pudding model. And that's because that was a really famous dessert at that point. But to me, like modern day, that looks like a chocolate chip cookie to me. So that's what he says. Then Rutherford comes along. And Rutherford does the gold foil experiment. So he assumes that atoms are plum puddings. That's what's thought at the time, right? So if I took a plum pudding model of the atom, with our electrons scattered throughout, and what he fires at it, he makes a very thin piece of gold foil. So the only reason he uses gold is to make it really, 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 really thin. And he takes an alpha particle. Now, an alpha particle is a big, heavy, positive lump that will come into with our physics paper 1. It's 2 protons, 2 neutrons. But the point of here is there's nothing to stop it, right? There's no positive to repel it. There's no kind of big lump in the middle. These tiny electrons are scattered throughout, right? It's like shooting a gun at the chocolate chip cookie. You wouldn't expect any of the bullets to ricochet. So what he does is he fires these alpha particles at it. And you can imagine them going everywhere, right? So the first alpha particle might say, go there, all the way through, no troubles. We go there, all the way through, there, all the way through. So far, so plum pudding's right. But then he notices something weird. Every so often, one will deflect off. And this is odd, right? He's got his detector and he puts his detector here and then he finds, well, let's just check around here. Oh, hang on. Every so often I'm getting one there. That's odd. And again, he puts his detector over this side and he notices some are pinging off that way. That's odd. And then every 1 in 100,000, it pings right back off where it came from. All right. Now, if I was firing like bullets at this chocolate chip cookie, I would assume there's something hard in the middle. And that's exactly what Rutherford does. He says there is a really dense positive charge in the middle of this. And he calls it, because again, scientists at this era just want to sound posh, so they use Latin words. So he calls the middle the nucleus, because that's a Latin word for middle, or centre. So he says, right, that plum pudding's nonsense. We're going to have a positive nucleus, and the electrons are just going to kind of orbit it, right? If I ask someone on the street to draw an atom, they will draw the Rutherford model. And then finally, the person who gets us to kind of this is 2 people. First person, the actual important person, is Bohr. Bohr says the electrons don't whiz around like that. They actually have these set orbits, and that leads us to all the bonding stuff that we had before. It explains that, so that's good. And the other person is Chadwick. And Chadwick, he discovers the neutron. So we go from, instead of just having this vague positive lump, we've now got protons and neutrons in that nucleus. And that's where we end up with our orbital model that we have today. Okay, so that's the first bit that we need to do. We've got a little bit of history. Then it's a case of just, it smacks the camera, look at this, amateur. Then it's a case of just being familiar with the particles. So knowing that protons have a charge of +1. Neutrons are neutral. They have a charge of 0. And electrons are negative, and they have a charge of -1. In terms of mass, the protons and neutrons, we say, have a mass of 1. And the electrons are very, 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 very small. 1 in about 1,800. But we don't really care about that. We call that negligible often. And that means so small. It's not 0, but it's so small I don't care about it. So we need to know those stats. That stats then leads us to when we look at the periodic table, right? So when we look at something on the periodic table, you have your symbol. So let's pick argon. So you have argon written underneath it, the argon. And then you have 2 numbers, 1 at the top, 1 at the bottom. Okay. Now, I can't emphasize this enough. The periodic table you get in the exam, it literally has a key which tells you the numbers. So don't sit there panicking which number's which, right? There's literally a key, okay? So use the key. But that 40 at the top, that's essentially our mass number. Now that's how kind of heavy it is, right? It's how much mass it's got. But if we go back to our stats, the only ones which actually weigh anything or have a kind of a mass is protons and neutrons. So if I'm weighing the atom, that is going to tell us our protons and neutrons. And if I look at the bottom number, we call that the atomic number. And the atomic number is just straight up how many protons there are. Okay, and these two numbers have an historical importance when it comes to the periodic table, which is the other part of this unit. Okay, so the first kind of ideas of the periodic table, people noticed that things started to repeat. Okay, they took all the elements, they almost played a giant game of top trumps, you know, where they've got like all the stats on the cards. They like laid them all out and they're like, can we work out some kind of pattern? All right. And the main person that we always like to talk about is Mendeleev. Okay, now what Mendeleev did is he first of all kind of ordered them by mass. Bear in mind, he does not know about protons. Okay, he doesn't know about neutrons, doesn't even know about electrons at this point. He just knows we're still at kind of the Dalton world of we can kind of weigh them, right? We can see there's some heavy ones, there's some light ones. So first thing he does is he puts them in order, all right? And then what he notices, right, if I'm going through the elements, I'd go, right, lithium explodes when it reacts with water. Beryllium, boron, carbon, nitrogen, oxygen, fluorine. Neon, doesn't know about neon at this point, but ignore that. Sodium. Sodium explodes in contact with water. So they've got similar properties. So it makes sense that they ought to be together in some way because they're kind of similar. All right. So what he does is he tries to combine the idea of putting them in order by mass, but also having the same properties. And that's where he lands with the kind of periodic table that we have today. All right, where we'd have lithium. This is now just me going to show off that I know the periodic table because I'm a boring person. Okay, and what he notices, right, is when he starts to do this, the columns start to now make sense, right? So these columns that we call groups, right, they have similar properties. Now he doesn't know why. Doesn't know anything about that. Right? Now, this is what he does. So the two things he does is he orders them by mass. He then kind of has properties in groups. But here's the actual real clever part that he does, right? When he gets here, right, he starts putting them in order. And then it turns out the one below aluminium, which is it's either gallium or germanium, right? So these ones here, they are gallium or germanium, doesn't know which. He realizes that the next one along, which is actually arsenic, right, which is a toxic non-metal, doesn't fit here, right? Doesn't fit here. So he's kind of like, if I'm doing it by mass and now I'm underneath and I've said that the properties are there in groups that should fit. The difference between the columns and groups, they're the same thing. So the columns are the groups. All right. That's what makes them, that's he calls the columns a group. So he realizes that these two here, this doesn't fit here. So what he does is he leaves a gap. So the actual brilliant thing he does is that he leaves a gap, right? And he says, and this is where he's actually really clever, is he says, right, I'm missing something here. This doesn't fit this pattern. I think that we haven't got one. We haven't got one. We don't know what it is, and I think it's going to be like this. And he does, and he predicts it, right? And then about like 2 years later, they find something which matches his exact descriptions, and then everyone goes, "Yeah, fair play, mate. Top work. You're right." Okay. So he's the first one who kind of really comes up with a modern periodic table. We've got the columns, which are called groups, and we've got the rows. Just to complete your question, Liam. The rows he calls periods. Okay. Now, how does this translate? Now, this is what he comes up with, right? He doesn't know about protons. He doesn't know about neutrons. He doesn't know about electrons. He just starts to know about these idea properties. But the beauty of it is it actually then explains when we start to actually know these things, right? So, what are the columns, right? Well, if I've got group 1, weirdly, that means it has 1 electron in its outer shell. So when you start to do them and you look at how many electrons they've got in the outer shell, group 1 has 1. Group 2 has 2, right? Group 3 has 3, 4, 5, 6, 7. Now, he actually doesn't know about these ones at the end yet, the noble gases. Now, the noble gases do nothing. They're boring. That's because they're already full. It's kind of like, when you had a nice meal and you're like properly nicely full, you don't want to eat anything else. You want to ruin that, right? So they when we go back to what we said with bonding, right? If we were looking for a full outer shell, they don't do anything because they've already got a full outer shell. All right, they just sit there. All right. So the groups have similar properties. Why do they have similar properties? Because of the electrons in the outer shell. The rows, the periods, right? How does that translate? That's how many shells they've got. All right. So if you're doing the kind of right, I've got like magnesium, right? I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, like that. That has got 1, 2, 3 shells, so it's in the third period. There we are. Okay. I haven't put in hydrogen and helium if you're going. That's the second one. So, and it's got 2 in the outer shell, so there it is in group 2. Okay. You need to know about 3 groups in particular, and then a kind of 4th concept for triple. The 3 groups that you need to know about is group 1. They are the alkali metals. Let me strip it up. Now, what defines these? It's the fact that if I chuck them in water, they go fizzy bang. Okay. So here on the first column, our first group has 1 in the outer shell. They are called the alkali metals. Group 7, let's mix it up with a colour. Let's go mauve. Ooh, delightful. Mix it up. I've gone from purple to mauve. Hang on, Karis, I'll get to that. So group 7, they are our halogens. Okay, now if group 1 have got 1 in the outer shell, given what we said about bonding, they're desperate to lose it. Group 7 has kind of got 1 space, right? They're missing 1, so they're like desperate to gain it. And that is what leads us to this, and we can go into why in a second. But as we go down the group, they get more reactive here for the alkali metals. So as we go down, they get more reactive. the alkali metals. But for the halogens, because they want to gain, the kind of opposite is true. So they get more reactive as they go up, right? Because these ones here actually are better at gaining an electron. Better at gaining, better at losing. And the last column that we need to know about, the last group, is the last one, which is the noble gases. Okay, and the noble gases, they do nothing, right? So it's group 0. They basically just sit there. They are unreactive. Why are they unreactive? Because they already have a full outer shell. Okay, the fourth bit that is triple only is the big block here in the middle, which has got stuff like iron, it's got stuff like gold, it's got stuff like copper. Okay, this big block here is called the transition metals. Okay, and all you need to know from a triple point of view is that they tend to make coloured ions, so you get pretty colours, lovely, and they're good catalysts. All right, so pretty much anything if you think of like a stereotypical metal, it's probably in there. To answer your question, Karis, about metals and non-metals, okay, there's a zigzag line which kind of goes on here like that, right? Your non-metals are up here on your top right. Your metals are down here on your left. Okay, so metals are kind of this way, and then non-metals are up here. Okay, is there any questions on any of that massive ramble? Right, so if there isn't, look, there's a lovely question here, Karis, which is beautiful, right? Perfect for you. It says here, elements are metals or non-metals. Figure 2 shows an outline of the periodic table. The periodic table is divided into sections. Where are metals found in the periodic table? So what sections are metals? I'll let everyone have a little think. I'll have a little sip. Sip from my sippy cup. Right. So we drew that zigzag line on there, didn't we? There. And we said metals are that side and non-metals are that side. So if I look here, that's going to be a metal, that's going to be metals, that's going to be metals, that's going to be non-metals. So if we look at the question, okay, it is A, B, and C. Yeah, so I think, Karis, you probably didn't know, because I hadn't put the options on there, you probably didn't know that you could go with more than one. But C is metal, A is metal, B is also metal. Okay, and then look, just to perfectly come on here from what we talk about with transition metals, okay, it says which two of the following are typical properties of a transition metal. Now, again, like I've said before, I know, right? You almost want to imagine I storm into the exam room like 10 minutes left and just shout sanity check at you. This says 2 boxes, right? It sounds obvious, right? It's like telling a year 7 that if you've put it under a Bunsen burner, it's going to be hot, right? And yet they still grab it. If it says tick 2 boxes, tick 2 boxes. Now, what are they? Well, metals. They're, as I said, think about a normal metal, right? So if this didn't say transition metal, it said what are the typical properties of a metal, right? You almost ignore that transition, right? Can be bent in shape, yeah, right? Good conductor of electricity, yeah. Low density, nah, they're heavy, aren't they? Right? Low melting point, nah, hard to melt. Poor conductor of heat, nah. Metal gets well hot in it, right? We bring it into that. Okay, right. Oh, there's a Q&A option. Oh, I know we've been doing it in the chat, but I didn't know. Professional streamer. I don't know how that works. Ignore that. Unprofessional streamer. Right, let's do a next topic poll. All right, now. Hello. Can I help you with anything in particular? So, right, our next topic, as I make the table wobble, is I can do some exam cues. We've kind of broadly done structure and bonding and atoms in the periodic table. I'm not saying we've covered everything, but we've broadly done all that. Do we do energy changes, or do we do chemical changes? So I'm not going to be ridiculous tonight. Look at that poll feature. It's huge. Exams next week. Go have a sleep. It's a Sunday. And what are you, like 2 hours ahead? It's like 10 o'clock. Right, I'll give the poll a little bit. I'm gonna sit on the hunt for a snack. Yeah, I've had too many crisps. Right. 8 o'clock. Right. Exam questions. Cool, let's do some exam questions then. Right. So let's do the one which is right in front of us, shall we? Good a place as any to start. So which diagram represents a pure compound? So people often get into a bit of a tiz about compounds and mixtures and elements. All right. My kind of tip with it is box it. Now, what do I mean by that? I'm gonna everything in there which is separate, I'm gonna put in its own little box. All right. I want to consider the own individual lumps, as it were. Now, the lumps are technically called molecules, but I just want to look at those individual kind of lumps. All right. Now, when surely both are the same thing there, right? I am a teacher, and I am teaching in the UK. So here, I've got, if I look in each box, right? That box there is a compound. Why? Because you've got two or more different ones, and they're chemically combined. Okay. Now, every box there is the same. If every box is the same, or molecule, right, is the same, then it's pure. All right. So here I've got every box the same, so it's pure, and those boxes are compound. So spoiler alert, that is the answer to this one. If I look here, every box is not the same. If every box is not the same, right? So if it's not the same, that's when we get a mixture. Okay. So here, they're not the same, so I know that's a mixture. Right? What's it a mixture of? Well, this one here is a compound, and that one there is an element, element being one type of atom. So that's a mixture of compound and element. Here, not the same, so it's a mixture. Within those boxes, I've got elements, so it's a mixture of elements. And here, that's a compound, that's a compound. They're not the same, so that's a mixture of compounds. All right. So I always find that the box it kind of technique is always just a little bit nicer. It's a little bit easier to look at because it stops you kind of confusing the mixture and the compound aspect. Which diagram in Figure 1 represents a mixture of element and compound? So look, by doing all that preamble, it then becomes obvious, right? So here we've got compound and element because that one's a compound, that one's an element. Each box is the thing, so therefore it's C. Sorry, Karis. This is IGCSE. Don't know anything about IGCSE. I mean, I presume it's just GCSE, but you look at it a bit more. So it's an I GCSE. I know it's international. I know what it is really, but I don't know the specification. I love the retraction, Karis. It's all good. You're allowed to make mistakes. Right, we've done the rest of that one. Okay. Into the world. Now, other thing which is in the kind of mixtures area really is how to separate them. Okay, so let's have a little time looking at the separating of the mixtures. Right. So in order to kind of work out what technique you're going to use, you kind of need to think about what you're dealing with, all right? Because the way that we're going to separate mixtures has got to rely on, right? So separating mixtures is got to rely on a kind of a difference, right? Because by having a difference, you can exploit that to separate them. So if I take something like sand in water, I'm exploiting the difference that I'm exploiting the difference that sand is a solid and liquid, and water is a liquid, right? And I can use that, all right? Now, again, just to clarify, right? I know IGCSEs are sat at the same time. I don't know the ins and outs of the specification of IGCSE. It's just AQA, GCSE in the UK. Lovely. International tonight, loving it. I've never felt more cultured. Right. So let's say I have got, I just mentioned that there, salt and water, right? Or sand and water. What's our difference there? The difference there is that's a solid and that's a liquid. And crucially, that does not dissolve in it. So we can say it's an insoluble solid, right? And that's a liquid. What technique would I use for that? I would use A, which is filtration. Filtration is great at separating insoluble solids from liquids. Okay. Now, if I had salt and water, I don't have a insoluble substance anymore. I have a soluble one. It dissolves. So what am I going to use for that? Okay, well, I need to again exploit one property, which is the fact that this is going to be harder to heat up and evaporate. So I can use crystallization, right? If I want to get the salt out, I can get crystallization. Okay, let's imagine then I have oil and water, right? Well, these are both liquids, so any of these techniques are now off the table. What's the difference in these? These actually don't mix, okay? So one of the things that you can do here is you can do what's called decanting. You let them kind of go into two kind of layers and then you pour off the top layer. You can also use something called a separating funnel, which looks like this. Okay, and then you let the layers form like this and you can pour one off. That's quite niche, not too worried about that. But those liquids mix, right? Don't mix. It's much more common to have liquids which do mix, right? So let's say I've got ethanol and I've got water. Now those two together, they mix. Okay, so to separate them, we do distillation. Now, what is the difference that we're capitalizing on there? We're still capitalizing actually on the difference in boiling point. Okay, that's what we're capitalizing on. So the water has a boiling point of 100 degrees C. Ethanol is about 69 degrees C. If I heat it up, okay, that's going to boil first, that's going to boil second. Okay, and what actually happens is when you look at that thermometer, it will kind of go up to 69 until everything's over, and then it will suddenly shoot up to 100. The answer is both. Pretty much everything we go through is both. Cool. And then this one here, our last technique, is chromatography. Now, chromatography is if I want to separate a couple of solids, right? So let's say the classic thing, this is again done more in paper 2. So the only thing you need it for in this paper is just knowing that it's a separation technique. But let's say I've got more than one soluble solid, right? Well, chromatography is a way of separating there. Okay, so the question says, which apparatus could be used to collect water from sodium chloride solution? So if I was wanting to collect the water, I'd use this one, right? Because here, the water's going to go away and I'm going to be left with the salt. But here, the salt's going to be left in here and the water's going to come over here. So we can do that. So that makes it B. And which one is filtration? Well, I've already kind of spoke about that one. That one is A. Okay. Came second in the poll. Chemical changes. Nobody likes energy changes. Right. Okay. Those questions. Right, this is something we haven't mentioned yet, actually, and this will kind of tie up the atoms in the periodic table in one nice kind of neater bow. It says, explain the trend in reactivity of the elements going down group 7. Now, I think it'd be harsh for them to ask this in foundation. Okay, it's kind of, yeah, it'd be really bold of them to do this in foundation. I'd say this is mostly going to be higher. All right. In terms of foundation, they'll talk about the idea that the reactivity decreases as we go down the group. So let's do that to start off with. Okay, reactivity decreases down group 7. Okay, that is the type of thing which they would ask any tier. What happens to the reactivity as you descend group 7? What's actually happening here? Right. If I was drawing them, right, so here is fluorine. 1, 2, 3, 4, 5, 6, 7. Here's chlorine. 1, 2, 3. Right, you got 7 on the outer shell. Here's bromine. 1, 2, 3, 4. Right, here's iodine. 1, 2, 3, 4, 5. Right, it's deliberately chaotic and unneat. Okay, because what am I trying to get across here? As we go down, okay, the atoms get bigger. Okay, now what's a better word than get bigger? That is the radius increases. Okay, so going back to the question, so our first bit of insight. As we descend the group, the radius increases. Okay, well, Going back all the way to the first thing we said that they've got they want to gain one. All right. So they want to gain. All right. They want to gain an electron. Right. Now, electrons are negative, right? So if I want to attract it in, I want the positive nucleus in the middle. All right. Now, if that electron is here, right? Oh, nice and close, lovely. All right. That is close to our positive nucleus, right? But now, if we look at iodine, right? Monstrous. Okay. Big old distance. So, right. So our next point is that they want to gain an electron. Okay. Oh, help that has been shot on it. Scuffed. Absolutely scuffed. Okay, so that means that it is if we have a larger atom, it's going to be less attracted to the nucleus. If it's less attracted to the nucleus, that makes it harder to gain the electron. If it's harder to gain, that makes it less reactive, as we have said. Okay. It's quite tricky, that one. Do not worry yourself if we find that particularly challenging. Right. Before I just ramble on chemical changes, is there a particular kind of topic that people would like me to cover in it? I know there's not overly many of you tonight, but if anyone does have anything particularly strongly in it, I can do that. Otherwise, I can just keep on cracking on. I'll tell you what, let's do something slightly on its own. Slightly on its own that no one's necessarily asked for. And that is quantitative chemistry. Now, but in particular, the foundation aspect of it, right? Foundation quantitative chemistry is really small. So you can really predict that this will come up. It's either going to be this or it's going to be percentage by mass. That's it in the topic, basically. So if you, this is one of those few things that you can genuinely kind of question spot, really. So it says here, calculate the relative formula mass of carbonic acid, and it's H2CO3, right? So what the relative formula mass is basically saying, how much does this weigh altogether? If I took them all, how much does that weigh altogether? All right. Well, the first thing I need to do is establish how many of each atom I've got. So I've got H and then the little 2. Remember, the little 2 applies to the thing just before it. So that applies to the hydrogen, not the carbon. So that means I've got 2 lots of hydrogen. Carbon, right? No number there, so there's only one of them. And with the oxygen, the little 3 applies to that. So that's 3 times oxygen. Well, then I can look on the periodic table, or even better in the exam, like they tend to just give it to you, right? So I've got H, C, and O given there. Again, remember, in the actual one, gives you a key. So don't be, if they don't give it to you, there's a key. Right, we're looking at the top numbers, we're looking at the mass, because we're looking at relative mass. Hydrogen is 1, so that's 2 times 1. Carbon is 12, 1 times 12. Oxygen is 16, 3 times 16. Then it's just a case. Notice how I haven't really I've written a lot, right? Proportionally. Some people really try and leap ahead. It's your actual GCSE. Why bother, right? Don't take those chances. Just say how many of each there are, put them in, do the first level of simple maths, and then add it up, and that's 62 grams per mole if you actually want a unit, but nobody really cares. Okay, there you go. Again, no such thing as a non-calculated science paper. Don't be afraid to put it in. Now, where can this go to? The only other thing that you can say is, what is the percentage of, say, carbon in carbonic acid? The first thing you need to do is exactly what we've just done here, the RFM. Okay. And then you look, because it says the carbon part, right? We then just look at the carbon part of when we were doing it. And you see that gave us 12. So the percentage by mass is 12 divided by 62 times by 100 to make it a percentage. Okay, and then you stick that into a calculator, work it through. Off the top of my head, that's going to be annoying. It's going to be roughly a fifth, so it'll be roughly 20%. Okay, it'll be like 19.1 or something. Okay, so that's the only other thing they can kind of go through in foundation. In terms of chemical changes, okay, well, I'll go through the rest of my exam questions I've got instead of just rambling. I'll kind of go through them, and then if we've got anything desperate at that point, then obviously I can answer it. If not, we'll call that a night, because I've already been rambling for an hour and 7 minutes. So, right. Okay. Right. Now, just to kind of continue on, this now then turns into a chemical kind of changes part of it. All right. So this was when we were talking about the aluminium one quite a while ago, right? Where we said aluminium oxide is an ionic compound, explain why aluminium oxide has a high melting point, and then it continues as such, right? So it was talking about how do you extract it, okay? This is the kind of bit is how you extract it, and we do that using electrolysis. But it's a little bit more complicated for aluminium oxide, and this is one of those named kind of procedures that they like to kind of go on. So with aluminium oxide, right, basically they have, with aluminium extraction, you have this kind of giant vessel like this with our like kind of electrodes in here like this, right? And you have to melt the aluminium oxide in here. So we've kind of got, I think they're all positive off the top of my head, and that's all negative. Might be the other way around. Anyway, the point is you've got that dipping in here, okay, and this has got to be molten aluminium oxide. Now, the thing about molten aluminium oxide, right, is first of all, you've got to melt it. And that requires a lot of energy. And if it requires a lot of energy, that requires a lot of money. Okay. You are then also going to pass electricity through it. I refer to my original point. Also requires the moolah. So if there's anything that we can do to kind of reduce that kind of energy input to get our aluminium out, then we're going to use it. And this is why they like to talk about it, because there is a substance that we add to aluminium oxide, and that substance is called cryolite. Okay, and what that does is that reduces the melting point of the aluminium oxide. So therefore, it's easier to melt, and therefore you don't need to spend as much money trying to melt it. Now, again, this stuff here is more higher tier, but I'm just kind of skimping through here a little bit, if I'm honest with you. Okay, it says the positive electrode must be continually replaced. Why? Okay, well, you produce oxygen at the positive electrode. The positive electrode is made of carbon, right? Well, I've got carbon and oxygen, right? And it's hot, so that is going to react with the oxygen. Okay, and eat away at it. It's going to react with the oxygen and make carbon dioxide. Yeah, I can do some electrolysis. That's no worries. Electrolysis is one of those things, though, where it's kind of at this point, it's a bit of diminishing returns. Like, if you don't fully understand it at this point, I'd spend your time on other things, because it's complicated, is the answer. And that comes from like kind of exam board kind of evidence. Right. Okay. If I look at, yeah, Will, I'm not saying I'm not going to not mention it. What I mean is it's like, as I say, I'm literally going through it now. But what I mean is it's like, it's one of those things where you could spend like 30 hours on it, right? And sometimes those like, we'll spend time on it now. If you still don't understand it, obviously you can try a little bit. But I'm not saying give up or anything. But we're at the time where we're the night before the exam. I would spend those minutes on other things. All right. So electrolysis literally means, okay, split with electricity. Right. Lysis means split, electro meaning electricity. So therefore, I need to have some form of electrical circuit. And we do that with the use of electrodes. Okay. And we'll connect them up to a battery. Okay. So these things here are called electrodes. Now, they come in two types, just because there's two ends of a battery. Okay. And to remember which one is which, we use the acronym PANIC. So the positive one we call the anode, and the negative one is the cathode. So this one here would be our anode, and this one here would be our cathode. Right? But if we remember from electricity, there needs to be a complete circuit. And at the moment, I've just got these two things stuck in here. There's a gap, there's nothing to conduct electricity. So we need to put something in between to conduct electricity. And that thing in between is the thing that you're going to split. We call that the electrolyte. Okay. And the electrolyte can conduct electricity. Okay. And it's the thing we are going to split. Okay. Now, because it can conduct electricity, you're kind of limited now into two things, right? You're either going to be a molten ionic substance, or you're going to be a aqueous, like dissolved ionic substance. And why are you going to be either of them? And that's because the ions can move. Okay, so in both of those situations, the ions can move. So in here, I've got a load of positives. Okay. Positive ions, and I've got a load of negative ions. Okay, now what happens is you end up with, let's say I now turn on the electricity, okay, the positive ions will go to the negative electrode, and the negative ions will go to the positive electrode, okay, so they go to the opposite. Okay, because they're kind of opposites attract. Now, what happens at those electrodes? Right, at the negative electrode, there is a load of, so here you've got lots of electrons, basically. Okay, and here you ain't got enough electrons. So what happens is these negative things kind of donate their electrons. They can then move through here, and then the positive things can pick them up. Okay. So what happens is this positive thing here, okay, the positive ion will gain electrons, and that will turn it back into its kind of atom, not an ion anymore. And the negative ion will lose electrons, and this again will turn it back into that kind of atom form. Each of these processes has got a name. Okay. Oxidation is what we call the loss of electrons, and reduction is what we call the gain of electrons. And the way we can remember that is the acronym oil rig. So there's levels to this game. If you are thinking more on the foundation aspect, it will be straight up what's made. Okay, so if I had potassium chloride, let's say it was molten, so these are the only ions here. We've got positive potassium, negative chloride. Okay, well, what's going to be made is this is going to have the cathode, the negative electrode. You're going to make potassium, and at the positive electrode, okay, you are going to make the chlorine is going to kind of undo itself and become, so the chloride is going to undo itself and get chlorine. Okay, that's the first level. Molten salts, the positive, so the metal will go to the negative electrode, and actually you'll get the metal. The negative ion will go to the positive electrode, and you'll get that turning. So that's molten salt. So that's kind of layer one. So layer one is kind of molten salt, and you're just going to get like what the salt is kind of undone, if that makes sense. Right, you're going back to the elements. What's the next thing they can ask? So next layer down on our like electrolysis iceberg is aqueous solution. Okay, now if you've got aqueous solution, let's say we're doing sodium chloride, right? Well, if I've got sodium chloride, I've got Na plus ions and Cl minus ions. If I now dissolve that in water, I've also got H plus ions and I've got OH minus ions. Okay. So the question then becomes, what do you make, right? Are you going to get the sodium out, or are you going to get hydrogen? Are you going to get the chlorine out, or are you going to get oxygen? Okay. Now, the rule is, at the positive electrode, okay, you'll make anything less reactive than hydrogen, right? Sodium, more reactive. Okay. I'll be honest, Zach, I've been through quite a lot. I'm already kind of getting to the end. I've been through everything. So afterwards, you can kind of like go through, okay, rewatch it if you want. This is also foundation combined, by the way. This is still foundation. So here, the sodium is more reactive than the hydrogen. So the hydrogen will be made. Okay, so in this case, you'd get hydrogen. Which goes to which? Oh, which electrode? Sorry. That's the negative electrode, isn't it? All right, the positive ions go to the negative electrode. And the negative ions go to the positive electrode. Okay, they always go to the opposite. We said here the negatives go to the positive, the positives go to the negative. Okay. Do you have any questions before I talk about the rule there? Is it a group 7 one? Was it in terms of electrolysis? Yeah, so you're thinking now of you're kind of getting onto this rule here at the negative electrode, aren't you? Sorry, the positive electrode. Okay. So at the positive electrode, basically by default is oxygen. Unless there's a halide. Now this is when you say group 7. That's the halide. Okay. So here you would get chlorine. Now, even though it's in paper 2, they sometimes ask how would you test for that, and you can get our damp litmus. Okay, get your damp litmus, and that will get bleached. It will initially turn acidic, it will go red, and then it will be bleached white. So the rule here is just if it's group 7, so there's a halide, it makes that. Otherwise, just go with oxygen. All right. So that's kind of the second rung on the electrolysis there. So at the negative electrode, you get the least reactive thing, which is pretty much always going to be hydrogen unless it's copper, right? Copper will be made there. And at the positive electrode, easiest way to say it is you'll just get oxygen unless halide. Okay. Now your next rung on that ladder is half equations. And that's actually what's going on at the idea, right? So if I think about potassium, right? So potassium is like K plus. At that negative electrode, it's going to pick up 1 negative electron. And that is going to make our potassium metal. And you can add state symbols, stuff like that. At the other end, okay, so let's say it was potassium oxide. Okay. The oxide is O2 minus. Okay. Okay, it's going to lose those 2 electrons to make oxygen gas, but it then gets annoying with kind of like state symbols and balancing and stuff like that. Okay. Again, if you're not happy with half equations at this point, I'd just concentrate on what's made. Cool. Does anyone have any final questions? Because it's 10 to 9, and I'd quite like to. I'm going to spend a little bit of relaxing time before. Cool. Any final questions from anyone? Didn't go through everything really today. We did a bit of electrolysis. We did our history of the atom. We started out with our bonding. We did our kind of like flow chart of bonding. We talked about reactivity in terms of group 7, and also by reverse, that'll be group 1. Spoke about the box technique to avoid silly mistakes there. Yeah, cool. So, unless anyone has any final questions, I will end the stream. Right, cool. Cheers. Have a great one, everyone. Bye.